So the method actually applies to many differential equations, like parabolic equations, and even sub-elliptic equations, systems, things like that. I mean, with BN, we did a lot of work in this direction. But let me show you the ideas. So the goal is to do this. If this is LP, I want to prove that d squared u is in LP. And this, as the Schauder theory, this again is a very precise estimate. Basically says the Hessian is in some space, equivalent to the trees is in the same space. It's amazingly strong theory, and actually a statement a little bit stronger than this, which has some connection what we did before. So let me try to do this equation instead, and the theorem would be this. If this is true, then that the gradient use LP norm, say Bao half, less or equals C, F's LP norm, plus some, say, use L2 norm or whatever, these kind of things. So that is the goal. So what's the main difference? The main difference to Schauder. I mean, I talk about the differences, the analytical differences, is that the holder has many point-wise understanding. I talk a lot throughout the years. There are many theorems like that. It says locally there's a way to understand like U is a holder. Then they are all equivalent if it is true, all points, all scales. But for LP theory, there's no way to do it. And how do you say at one point a function looks like LP function? That's certainly impossible. That's the problem. But we want to do it anyway because this is correct, right? So how do we prove it? Actually, the most important thing about proving this is not how to prove it. The really important thing is that how do you understand? How do we understand LP norm? So I always go back to holder. Holder is, say, I can draw a picture. Right? It's geometrical decays with respect to distance. That's the holder. But what is LP? So this is easy, right? Basically related with this picture. Then what is? Let me take P equals 1 or 2. If I tell you this equals 1, that is the question. And how can I tell you a function's L2 norm equals 1? Then if I tell you L2 equals 1, what have I told you? What's the information contained in that sentence, right? The picture on the right is holder, but if I tell you a function L2 norm equals 1, that's basically the question. Then yesterday, I said this is true, right? This theory infinity T. I say ball 1 here. This is true, very precise, and also this is true. Say this decays like 1 over t squared, and this is a little bit better than that. If this guy decay like 1 over t squared, of course the integral still infinity. It just barely fails the integrability. But this is the precise information. So, and if that is all you have, of course, you say, if I say L2 equals L1, it says that at least says this thing, right, goes to 0 at some speed. And this speed, I cannot say only one level, but the speed of this goes to 0. I would say the LP-ness of this function. You kind of agree, right? It's because I cannot really say it. And only this one and the decayness, they are related. And if this decays faster, actually that's increase this 2, right? And that's the information. But that's correct, but still fails to tell on the intuitive level. But let me play a game. So this is the important thing, first of all. Then this would be a measure, right? But what's the intuition measure? How do you understand measure? Let me draw a picture. Say here is a unit ball, right? What's that mean? Goes to 0. I see a very tiny little set. Say u less or equals to 100. I mean this set can be anywhere. And the tendency is that higher the level is, the smaller the measure. Here maybe u is like a bigger equals 1. I mean this will be bigger set. Somewhere u is bigger equals like 10 to the 6, even in a smaller set. I mean that's basically you see the higher the level is, the smaller the set. Maybe you're very satisfied with that picture, but the picture is wrong because I'm not sure I put that set there is correct or not. Certainly it's not correct, even though the problem is more serious. Let me play a game. Suppose here u is almost like 1 here, right? Suppose here is almost like a million. I mean, right? Suppose they have the same measure. Then if I swap the value, where it was 1, where it was a million, just swap them. And before it was a million, I define it to be 1. Where is 1 million? 1 I define like a million. Then I compute the L2 norm. What you got? Exactly the same, right? The LP norm is blind to pointwise value. So the information about this 1, I don't tell you where the function is huge, where the function is small. I only tell you the measure. What is the understanding? So that is correct all the time, which is invariant with respect to this kind of swapping. Now actually, I would propose that the correct understanding of this picture, you always win, is not where the function is big, where the function is small. It's the probability of random choosing x. Then what is the probability for that value to be big or small? Which is exactly correct. It's invariant, right? So this only tells you that the tendency of the value, where it's big, where it's small, doesn't really tell you where it exactly. So to prove LP estimate, you shouldn't think about something really, really precise. You want to say that you measure the chances for you to huge, big numbers will be small. If you can do that, that's LP estimate, right? And that's correct because you saw it. It's what you want to prove is the probability for x for random choosing x, so that it is big, has a small probability. You don't have to do anything else, and this x is random. So So this bigger than t is basically maybe divided by that. This is a physically and mathematically correct statement. Is the probability of a random x so that u of x is bigger than t. It's really true. And that is the understanding. And what you want to do is you want to show the probability for x. So the gradient is bigger, is small. So the x has to be random. Now, let's try to prove W1P. So the first question you want to do is you look at this equation, right? And also you need iteration. The power of mathematics is iteration. You don't want to hit it at the beginning. You want to attack it slowly. So you have that PDE. The easiest available thing is everybody knows. This is easy. Actually, the constant is 1. Right? This is easy. This lemma. You can do it like close your eye. You can do that. And what do you want to do next? So if LP is true, you try to more or less prove that the level set of this. If you can prove this, then you are done, right? If f bigger than t. The distribution really proportional. They related. You just take integral. You are done. And actually the idea is to try to find more and more points so that gradient u is safe, finite for random choosing x. So you look at this guy say there. I give you typical f is in L2 or in L3. Suppose for the time being u is in L3. The f is L3. I want to prove gradient u is in L3, for example. So now I pick that point. You cannot pick the point specific. It's just there, exactly at that point. So what do you see? What is the typical behavior of a randomly choosing point? If x is random, I can 100% guarantee you that this actually, I cannot do that, but this will be correct. Right? I can guarantee you it's finite, because this estimate, right? If random choosing x, it will be finite, right? But not quite qualitative, but at least it's finite. That's good news. Actually, you can do a lot better if x is finite. You can make sure x is a Lebesgue point of gradient u. So it's not only finite, it is nearby infinitesimally is finite. It's a lot of finiteness near that point. I can 100% guarantee you that is correct. But if you recall the proof of a Lebesgue differentiation theorem, this is saying this Lebesgue, there's no control of the neighboring behavior, and those kind of things they are nicely stated and very, very nice, but hard to use analytical. I want the control for a fixed level, and then there is actually another lemma, and actually people use this idea even when you prove the Lebesgue lemma. is if you random choosing x, I can guarantee you that point is not only the big point. I can make sure that it's qualitatively small in all scales. This is the discovery. Let me say a definition. It's a Hardy-Littlewood Maximum function. This is the following. It's I give you a function f. I want to choose x at random. But I want to make f study his local behavior near x. I define this. Take an average dx in R. So what it means that instead of trying to say that function is the big point, and the big point give me a tiny little scale and is uncontrollable, I don't want to do that. Instead of saying the value of there, I replace the value by all the, because I don't know which scale is correct. So what I do is I consider all the possible scales, including big and small. This is a lot bigger than f, right? This is a lot bigger, seems a lot bigger. This I say bigger seems bigger than f(x). But this amazing thing discovered by Hardy-Littlewood that if you look at this function, it's basically the same thing as f, and it's the next lemma. Is this true? Because everything is controlled by this guy is always positive anyway. And this actually in Rn is like it's so what that tells you? In the case say f's L1 norm is 1, right? If I take n equals a huge, this will be small. Then this means this we agree, this is a probability. The probability of a random choosing x so that the maximum function bigger than t has small measure. And you have to understand this other way around. The other way around, the random choosing x, you are almost guaranteed that the maximum function at that point is finite qualitatively by a finite number, right? It's really qualitative. I can control that. And not only that, the next line even amazing is that this thing is true. What the second line tells you? The second line tells you that the probability distribution of the f itself and the f's maximum function, they are exactly the same, right? They are exactly the same. And that tells you that when you understand a random choosing x, you can understand how big f at that point is by the value, or a much better way is by the maximum function, right? I mean, you just psychologically switch it. You say f at that point is 1. I can either understand that statement as the value, even better is at that point is his maximum function. And the maximum function analytically is much stronger, much more control give this function. It makes the point control and the point-wise control and local control, they are all equivalent. For example, you can see that if a function say at a point, the maximum function is less or equals to 1. Okay, this means the integral in the unit ball nearby is less or equals to 1, right? Then you have a lot of points that less or equals to 10 nearby. It's amazing picture, and they all carried by this inequality. So if you like it, I won't put it for you, but it's really elementary to prove it. Actually, later on, the computation really shows the proof of this. But anyway, that's to be I think, should be correct physical understanding or correct geometrical understanding of LP space. So to prove LP, first of all, there are two psychological things. The first psychological thing is that you don't try to prove LP, you just try to find more and more points is under control. You want to do that. Second thing is that the points under control, you better use maximum function because they are the same and much better. And following that idea is you want to do the iteration. Iteration is to say LP would be same thing as to say the maximum function. I'm proving this LP. This function has a bigger controls. I want to say this huge number. If I can prove this, I'm done. It's much smaller than this. This is the fixed. Much smaller than the maximum function green inverse square bigger equals 1. Plus some error term. I mean those errors is like under control. And that's exactly what I want to show. Okay, so what I want to show is that that's clearly iterative, right? From one level to a huge number level, and that is nothing to do with PDE actually. Then the infinitesimal equivalent statement of that is actually this following lemma. In order to prove that, is I start with a typical situation. So I look at my ball 1, then I pick a point. Just exactly that point. What do you see? You can make this correct. Is that there is a point actually in ball 1, such as say the maximum function of this guy at that point is less or equals 1. This is typical. No? Then actually I want to say this for any epsilon positive, there is delta. The delta actually equals to like epsilon over C0, and this n is fixed. This n is that n. Such that this following thing is true if Laplacian U equals to F. I mean, all those things are physical constants. With in huge domain, omega contains like a ball 5. I mean, this you assume the equation holds in a big place. Then of course you make the things like a shorter theory. I make it a small L2. I mean this divergent of F. Say ball 5. This we call it delta. Then the following is true. The maximum function of gradient U squared bigger or equals to this n is almost like a nothing. And later on I will change that condition a little bit, but this basically says the following picture. If you see at one point is typical, then if the L2 norm of F is almost like a 0, then your chances for the gradient U to be bigger or equal to a fixed typical number, almost 0 probability. Of course, then you win, right? And the thing is that the proof of it is really trivial. It's like one line proof. Then I will do that computation. Maybe let me make this. Let me assume this is true. Also assume that is true. Then I kind of prove it. First of all, this condition, you can make it more inductive by assuming the following, by assuming like the maximum function of f at the same point to be less or equals to delta. I mean, this clearly implies that, right? I mean, the maximum function means in any scale, any ball, the average less or equals to delta. This will be less or equals to. Maybe you can change it to a constant, but that's small is small. This really implies that. Then this statement there is a major theoretical nonsense. Implies this from here implies this statement. There's this epsilon. Maybe there's another constant plus m the maximum function of f squared bigger or equals to delta. I mean, this implies this. This is lemma 1. But let me first, from lemma 2 implies the theorem. Lemma 2 implies the theorem. Lemma 2, you see that is really intuitive. This is like an almost like this number. I mean, suppose this is true. I mean, it's like, but I want to emphasize this is fixed. Why this kind of thing is possible is actually, if you take delta equals 0, right? Then what do you see? You see U is harmonic. If U is harmonic, and the maximum function is bounded by 1, then use any norm is under control. U will be smooth, right? U is smooth, then actually this number will be always bounded. So you take n sufficiently large, fixed, this will be empty set. So that's likely to be true. So in general, there's a small perturbation of that limiting case. So why this implies the theorem? Then you do the scaling. If this is true, then this is true, right? You put a t here, t there, t there. Because everything is linear. Then this is exactly our dream statement. If this thing is not there, what do you see? I mean, this is iterative things. If this term is not there, you exactly says that the distribution function of gradient u square, that guy's maximum function is controlled by f square's distribution. So whatever this f square lies in, then gradient square lies in the same space. Then that's the proof. And it's easy algebra. If you epsilon sufficiently small, if you do the iteration, that won't hurt you. Right? You believe me? Yeah. Or you can say, both sides, you try to compute W1P norm, multiply by T to the P minus 1, integrate. Then this gave you LP norm. In this case, maybe PO over 2 norm because this is square. Then this gave you same kind of norm. That gave you F's LP norm. But there's epsilon. They get absorbed. But this statement actually a little bit stronger than that. If you do that, this actually called good lambda inequality. If you prove that way, you need gradient U is in LP. Actually, you don't have to assume it. If you iterate this in discrete fashion, you can literally prove the function has to be in LP. So anyway, this is easy. Okay, that's you just the easiest thing you just multiply T to the certain power, integrate, then you get the LP estimate. So the crucial thing is this, and from here to that. How do you see that? First of all, so proof lemma 2 is trivial. From lemma 2 to the theorem is almost trivial. Then let me show you that proof lemma 1 is also trivial. How do you prove lemma 1? So you want to prove that under this condition, this one smallness condition, another normalization condition, under these two conditions, the points, the chances for gradient U to be bigger than fixed number is almost like 0 probability. So then what's the situation? So if the proof of lemma 1. So you have this maximum function at one point less or equals 1. So this is bigger or equal to, you can choose any ball, say ball 4x zeros average gradient U squared. Yes, right? It's like by definition that's so at least says that you have energy control, and you also see that by the same token, this is true. So at least says that this f in that norm is almost like is almost like a 0. So then what do you see? You see U is almost like harmonic. This is almost like a 0. So you let the harmonic function help you. What is the harmonic function? Maybe U1 equals U on the boundary. Say ball 3. I mean this is 0, and this is here. I mean you have a huge ball. Then you can pick it anyone you want. Then what do you see? You see H and U, they're really close, right? You see Laplacian of U minus H. But from a boundary here, the influence from here to inside H is high frequency. It's low frequency. It's like it becomes smooth, and all the high frequency things is controlled exactly by this precise f. So I did that. I mean, this is very easy to remember. There's nothing to remember. So I have that. Then by the energy estimate, I knew gradient minus h squared or 3. Let's go see f squared. I mean, I'm sorry, like big F is little f. So ball 3. So this less or equals to like c delta or c delta square. C delta. So basically they are basically like nothing. Then I localize it. Say I can say ball 1. It's the same thing like a shelter theory. When you localize it, what do you see? If you localize, you see gradient h L infinity will be bounded by n. Right? This is universal, independent of anything, because harmonic and the energy is bounded by 1. Then that. So now that's basically a number you don't really care. Then this bigger equals to say 1/5 to the n t x in ball 1, the maximum function of gradient u minus gradient h squared bigger than t, right? That's the lemma for any t. The keyword is local L1. So now I look at this. Then there's a little bit technicality, is that like the fine print of what is the maximum function. What does maximum function means? The maximum function, if I say as I stated, is usually I define this like global maximum function. If this is locally defined, I define this maximum function of f. F say, let me put the omega here. Is indicator function of omega. That's easiest out. Here, the h this function in outside small ball 3 is not defined. Let me maybe I need 2, but so outside ball 3 is not it's not defined. So let me do it here. So so the maximum function, if I say this way, it's not quite rigorous. So let me say here is a ball 2. So this maximum function only makes sense. You draw this thing. Here's a ball 1. As I say, a good point here, or these are the bad points has small matter. A good point means I take averages all the way when the tangent here. That's good. And this actually means you go outside is fine. Go outside it doesn't tell you anything because it's like it's not you. It's unphysical. It's like but this maximum function give you the estimates if you look at how big the function is up to this scale when this two tangent. But when it's bigger, you have to rethink about it whether really you can do it or not. Actually, this doesn't matter. It is a suppose you look at a point in the complement of this set. Pick any n. Right now, I can fix it now. Let me pick the n that pick the t bigger than this number. Pick the t like twice of this 2 and 0. Then I fixed. I never played with this number 2n squared because that's just unfixed. Then this will beat this term. So this acts in ball 1, and the maximum function of this gradient u at most like n. So this kills that. Then I get maybe 1n. Then I have this correct inequality. Then, but the only thing is that I have this kind of control. The maximum function, the radius, I'm allowed to you can go anywhere, but go out does not make much sense. So say the good point, you can go all the way when this tangent to the second ball. Then you want to say, how can you change to the classical, where you start out with that definition, the global defined maximum function from what you see. And actually that's easy to do because this is a good point x here. There's another point because the condition says it seems impossible to do, but the condition says that there's another point x 0. If you look at the averages in all the balls, even go outside, I mean omega is huge. Omega is like almost like a universe. You draw those kind of balls, no matter how big it is, the average center at that point will be less or equals to 1. Right? That's the condition. But when the ball is big enough, right, from a good point, this x, to the point of ball 2, this at least 1. So if you move this ball to the point of x 0, if at x 0, the average less or equals 1, then the average among this x, when the radius is bigger or equals 1, will be under control. I cannot control really tiny. For the big ball, it's controlled already. You don't have to worry about it. So using this estimate about x 0 controls the averages at any other point. The average is not small one, not a infinitesimal like that kind of small. But when the radius is big enough, the maximum at that point is already under control with a reasonable constant. You can do the computation like what I did for the Carbonado embedding theorem. You can switch the centers. Then it means that for this kind of things, the bed point is small. Then the thing you want to you can switch this definition of maximum function. Maybe you want to take that number a little bit bigger, but everything is fixed. So this is ball one. The global defined maximum function gradient u squared will be bigger or equals to. You have to really see this when the ball is getting bigger, how big it is. Then it's bigger or equal to this number, maybe twice of that, and maybe the max of the other two numbers. The other two, like a 2 to the n would be fine. This less or equals to this c delta, maybe on the left hand side is 5 to the n, and this is your epsilon, or you just define this to be your epsilon. Then that's it. So as a maximum function, there are two scales. One scale is you look at the careful scale. One is a scale like you don't have to look at the careful, like bigger scale. The bigger scale already done. It's totally locally not that clearer. Then this says that the bed points above this level will be almost zero measure. And from this one to this to the inequality above will be also a kind of easy to prove. Let me draw this picture. So first of all, what the lemma 1 means? This lemma means that let me scale that lemma. The scaling is that if there's a 1 point x in any ball R with any center, if there's one ball such that there's 1 point so that the maximum function of f squared less or equals to 1 intersect with the maximum function gradient u, this less or equals to delta less or equals to 1, is not empty, means there's 1 point, right? If that's true, then it implies that the whole ball the ball R intersect with the maximum function gradient u squared bigger or equals to n is less or maybe let me say strictly less than epsilon ball R, right? It means that scaling, and this is equivalent to the following statement. Is very closer to that. So if this is not true, if let me put it in another way, is this m squared bigger or equals to n if this thing is bigger or equals to epsilon, then this couldn't be true. If that couldn't be true, means that the whole ball R is in this lower level set. In the complement of this thing, so it's bigger than delta plus the complement would be union, right? Right? This for any ball Y. That's logically equivalent statement. So let me draw a picture. What that means. Then when I draw the picture, let me only look at the main term, not look at the noise. And let me assume this is my noise. This is my, say, unit ball. Let me go back to the unit ball. U is defined huge. This is omega. Then this is my set. Gradient U is bigger or equals 1. Understood? I didn't write the maximum function, but everything is understood like maximum function. But that's the correct physical understanding anyway. Then what that estimate says is that, of course, this contains a set gradient U or his maximum function square bigger or equals n, right? I mean, maybe square root of n. Let me say square here, so make sure it's really close. So what that statement says that if I draw a ball, any ball, I mean this ball Ry can be anything, right? If the density of this set, what that means? The density of this set in ball R is bigger than epsilon. If I cut by a ball, is that epsilon fraction of it is bigger than n, right? The conclusion said the whole ball should be in the one level set. Right? I draw a ball. If that's cut at epsilon, that's exactly this picture. If cut by epsilon, then the whole ball is in this one level set. Right? And what do you want to show? You want to show one level set is bigger, a lot bigger than n level set. Which you couldn't say. You say n level set is much smaller than one level set. You want to show decay. And this picture shows the decay. You see, if I cut by epsilon, right? From epsilon, I expand it by 1 over epsilon. It's a huge explosion locally. Of course, this set will be bigger than that. So I can draw a lot of tiny little balls, right? I mean, here maybe I can draw a huge ball. Then this whole set is in one level set. Right? I draw a lot of those balls, and here the ball might be go out, but doesn't matter. If this beat my epsilon, then the whole thing actually in one level set. But then I say this is good enough also. I have this huge picture in front of me. Then next, what you do? The thing is, we play with the probability, and the shape of the set can be arbitrary. But then there's a smart Italian mathematician called Vitali to help you to have an argument saying that from each infinitesimal there's an explosion, then the whole set is explosion. What he did is you just choose the balls so that reasonably disjoint and covers the whole set. The Vitali says you can do that all the time. So what you do, Vitali says that you can choose the balls so that all will disjoint actually. I won't do that. I mean, this is wrong picture. It's there. So Vitali lemma says, I mean, near the boundary, you have to think a little bit. From here to here is explosion. Then from here to here is also explosion, because look at that picture. It says that. I mean, of course, you always assume that center of the ball is inside unit ball. Otherwise, it's really tangent. It won't be the case. So Vitali lemma says this picture shows that the maximum function, this bigger or equals 1, x in the unit ball is a lot bigger. It's basically 1 over epsilon, but there's a dimension like a overlapping business, and there's a business near the boundary. If you take that into account, Vitalis lemma is 5 to the n here, but near the boundary you lose another constant, maybe 2 to the n there. Then bigger or equals to next level. And then of course you add the noise. This is basically you don't see it. I can write down the Vitali current lemma. It's here. Is this is if A is a small, then A is, very, very tiny measure A is in ball 1. The following set has huge measure. What you do is you consider union of all the little balls. Y is in the union 1. Whenever ball R of Y intersect with set A in A, bigger or equals to epsilon. You epsilon fraction. Whenever that happens, I collect those kind of balls. So locally, if you have exact identity, it's 1 over epsilon expansion. Then this thing, measure that, has basically 1 over epsilon, but maybe 10 or 10 to 10. You need this is small, otherwise you get this number bigger than 1. That's impossible. You need this small because of this. Totally not very. It's totally for trivial reasons. So this like really the integration. You have the pointwise a kind of explosion. Then globally is explosion. But when it has a globally explosion, then you run this at all scales. Then that's the proof. And then this Vitali, you can prove it as the run the classical Vitali carving argument is you choose a ball, so total measure and the disjoint measure, they are comparable. Then whenever they disjoint, then you have measure expansion by 1 over epsilon, precisely 1 over epsilon. Then the overlapping, you miss a factor of it. And that's why you have like 5 to the n. But near the boundary, maybe you lose another one. How much is a fraction? How much gain you have from this tiny little measure to that measure for balls like near the boundary? You see like at most 1 over epsilon 2 to the n, maybe 2 to the 4 to the n.
Right hand side, left hand side. Every time.
This is this is other way around, right? This is right. I'm sorry. Yeah, this should be less or equals to. This would be minus sign, right? But anyway, this is. It's good you have a good student there. And this is delta T. Right. So use higher level set is controlled by the lower level set with very, very small factor. Then that's the LP. It's basically this is a tool you can change from L2 estimate into LP estimate. And whenever you have energy estimate, and a local regularity, exactly like a shelter proof, then you have a LP.